Just charm. All right, 1A.1 function relationships. And we're starting with linear function. We're going to put it in friendly terms, the definition of a linear function. A, relationship between two quantities. Anyone knows what we typically call those two quantities? Like what letters do we usually use to represent those two quantities? X and Y. X, comma, Y. With a constant rate of change. All right, so constant rate of change. When you hear that, what do you think of? What magic word should come to your brain when you hear constant rate of change? What'd you say? Mm-mm. Yes, that's the word I was looking for. I was looking for that magical being. So when we hear the words constant rate of change, we should think of slope. Okay. That's what we're referring to. Okay. That's a big characteristic of a linear equation or a linear function, I'm sorry, is that it has a slope. All right. What is another characteristic of a linear equation? Linear function, sorry. Has what? The equations. The equations are, there are three equations that represent an equation of a line. Does anyone remember? What is the first one that comes to your brain? Y equals mx plus b. So we have y equals mx plus b, right? That's one equation. That's one characteristic. What's another one? The next two are not most commonly used. Do you guys remember ax plus by equals c? Standard form? Okay. And then the last one is point slope form, which is y minus y1 equals m times x minus x1. Do we remember those three? Those three characteristics? Somewhere in there? Maybe have some cobwebs on them still? Yeah. All right. And then the other key feature of a linear function is that it's non-vertical. The graph is non-vertical. Is non-vertical. Meaning it can be slanted, it can be horizontal, but can it go up and down? No, because then it's not a function. Okay? So what I would like for you to do is come up with your own example of a linear function. All right, so at the bottom, you're going to create an example. I'm going to challenge you to write an equation and draw a graph. So create an equation of your choice and a graph of your choice of your linear function. You're going to draw your example. Which part? Graph is non-vertical. Again, it's your example. So as long as you're fitting those characteristics, is it a linear function? Yes. Well, I should remember, graph is a non-vertical line. Sorry, I didn't write the word line. I'll write it when I make my way back around. And when you create your equation, you have three models you can look at for that, right? To create your equation from. Doesn't matter which one you use. Just pick one, make it your own. Now, I want y'all to be a little creative. However, I respect people who just draw horizontal lines. I respect it. I get it. All right, who would like to share their um, equation example with us? Nobody? To the cards I go. Or someone just tell me. We got one. Y equals 2x plus 4. Is that a linear function? Yes, it satisfies our requirements for our equations, correct? All right, beautiful. And again, your graph, so I'm going to draw my XY plane, XY axis, X axis, and I'm going to just draw a non-vertical line. Guys, that is a pretty straight line. I just want to try to acknowledge my line. Um, this doesn't happen too often, and I need y'all to see that that is a pretty straight line, freely drawn by me today. So there you go. Thank you. Thank you very much. Okay. There's my two examples. Non-examples. We can come up with those out loud. What would a graph look like? It would it would be a vertical line, any vertical line, right? That's a non-example, correct? Okay. What about an equation non-example? There are infinite amount of those. I could write y equals the square root of 2x. And is that a linear equation anymore? No, it's not. It's now a radical equation, which we will learn about later, but it's no longer a linear equation because it's not just 2x anymore. It now has a square root. Okay. All right. So that's linear function. Yes. Up next is quadratic function. So we're going to put quadratic function in friendly terms. Okay. A quadratic function is still a relationship between two quantities. And what are those two quantities called? They're called X and Y. However, it's with a linear rate of change. So it's not a constant rate anymore. It's now a linear rate. Okay. So when we say the word linear rate, we're going to talk about what that means. So a linear rate. That means that to get from one point to the next on your quadratic formula, it follows the rule of ax plus by. So you're not just adding or subtracting to get to your next point. You now are possibly multiplying. Well, you're multiplying and then also adding or subtracting. Okay. It has a unique shape. Does anyone remember what the shape of a quadratic function is called? It starts with a P. Parabola. If you need help spelling it, parabola. Okay. AX plus B. No Y. Parabola is how it helps you spell it, but it's parabola. And you can have a happy parabola which means you have a positive quadratic, or you can have a third quadratic, which means you have a negative quadratic. Okay, there are three forms of a quadratic function. So first one is our standard form. Standard is ax squared plus bx plus c. Sorry, I forgot to write y equals. Does that look familiar? Remember that one? Ax squared plus bx plus c. Okay. One that you probably did not fully address in Algebra 1. I'm going to write it using f of x. F of x is just y all fancy, right? And it equals a times x minus h squared plus k. This is called vertex form. What it tells you is what the vertex is of your parabola. And your vertex is either your high or your low point, right? It is a k. And then our last form is going to be our root form. And root is a times x minus r1 times x minus r2. This one will be new to you. It will be something we utilize, not something that you have done before. It's called root or factored form, depending on who's telling you. All right, so knowing what the equation and the shape of a quadratic look like, could you draw two examples? A graphical example and an equation example. Yes, that's because your variables, your coefficients and constants can be anything, right? Your A, your B, C in standard form, your A, your H, your K. It can be whatever you want. So take this moment and create your own equation and create a graph of a quadratic function. So when you graph that, this will either be one of these shapes. So when you graph, once you make the numbers for A, B, and C, right? All right, make an equation for me. Y equals. That's, I want you to actually graph it. Oh, like graph it. Graph it for me. Tell me what it is. Okay. So you put your X. There we go. Write your X. Now we're going to graph it. How do we go to graph it? There we go. So notice the shape of it is a. Okay. I just showed it. Yeah. Or you can draw any shape of parabola. But that's what I wanted you to see though. So that's if it's in that format, it's gonna make that parabola shape. Okay. All right. Okay, friends. Let's look at these examples. Someone give me one of your equations.
Y equals 5x squared
plus
7x.
Perfect. Oh, I'm just gonna let y'all know sometimes my pen does what it wants and it just keeps doing it, just to keep us on our toes. It's crazy like that. Just gonna erase that. It wasn't me, it did it. So we have 5x squared, I'm sorry, plus 7x plus 1. Perfect. Okay. All right. And then when you draw your graph, it can be anything as long as it's in what shape? A U shape, right? A parabola. So no matter what you did, as long as you created some type of U, whether positive or negative, you have a parabola. Example. Got it? All right, our non-examples. So our non-examples would be anything that doesn't fit those characteristics correctly. So, for example, if I just took away the 5x squared, the first term of this equation, is it a quadratic anymore? No, it's now linear. What if I had this graph and I have multiple u's in it? Is it a quadratic? No, it's not. It's actually called a polynomial, which is the family of quadratic, the, the family that's part of, but it's not a quadratic because I have more than one max and min, right? All right. How do we fill out a quadratic function? The x squared is key. Yep. Without that x squared, then it is not a quadratic. All right. Up next, we have our exponential function. Okay. Our exponential function is a relationship. Oh, time for fillings. Between two quantities. And again, it's going to always be x comma y. Now, exponential is a little different of a situation, okay? It has with a constant ratio of growth or decay. So it's with a constant ratio of growth or decay. All right, so if a constant rate means you're adding or subtracting the same value over equal intervals, what do you think a constant ratio means? A ratio is a comparison. Another way of saying fraction. And a fraction means two things are taking place. Well, we've already used addition and subtraction, so ratio must be division and multiplication, that process of elimination, right? So a constant ratio means that, so when we have a constant ratio, that means that there is going to be something that is constantly being multiplied or divided. Make sense? So to get from one output to the next over equal intervals, I'm either multiplying or dividing repeatedly. Okay, so we're going to talk about the shape. First, we're going to describe growth. When it's a growth, it looks something like this. And when we have a decay, it looks something like that. Okay, another big characteristic of exponential, it is, I can never say this word correctly, so don't judge me, asymptotic. I think I said it right. Asymptotic. Okay, that means that it has a limit. Okay, this, they're going to have horizontal asymptotes. Horizontal asymptote.
And I just went straight to lunch.
All right. So asymptotic behavior, and then where was I at? The equation. There is an equation for it, and it's going to be f of x equals a times b to the x. So notice now that your x is the power. Okay. When it's exponential, your x is going to be the power. That's what changes. All right. So just for the sake of class, we'll do it together. So f of x equals 2 to the x is one of the most common exponential functions. Okay. The reason why this is common, it's because it's saying that your function is doubling in value every hour or every minute or every whatever. So we're going to draw the table so you can see what that means and what that looks like. So if we have x, y, let's say we have 1, 2, 3, 4. So you're working or you're growing. At hour 1, you're at 1. Because it's 2 to the x, that means that you're multiplying by 2 to get to the next hour. So 1 times 2 is going to give us 2. 2 times 2 is going to give us 4. 4 times 2 is going to give us 8. Does that make sense? That's what makes it exponential, is that you're multiplying or dividing over an equal interval to get from one value to the next. Cool? All right, your non-example, you have 2 other things that you can pull as non-examples. Again, you can be creative or you can be like me, and I'm just gonna do something random that's gonna be obviously not obviously not an exponential function. That's what makes it a non-example. So whatever your heart tells you to do for your non-example is up to you. You can draw a quadratic, you can draw a linear, you can draw some stars. No, I'm playing, don't do that. Still keep it math base. All right, so do you feel like you've been informed or refreshed on linear, quadratic, and exponentials? Awesome sauce. Okay.